Assalamu alaikum wa rahmatullah. Welcome everybody for today's experiment is weighted wall experiment. Weighted wall experiment, the objective of this experiment is to determine the overall mass transfer coefficient. As you know, as engineer, in order to design a packing column, the most important part is to determine the height of the packing. So in order to determine the height of the packing, you need to find KOG or KOL. So this is the overall mass transfer coefficient. And other parts, you can, from the integration of this equation, you can find the height of packing. So in this experiment, we want to determine the KOL and KOG, the overall mass transfer coefficient for gas phase or liquid phase, in order to use it later to design the packing column. As you can see from this equation, for G is a gas flux and L is a liquid flux, and A is the packing density. And this comes from the equation area of mass transfer equal Z, the height of packing, A is the packing density, and AC is the cross-sectional area of the packing. Of course, Z is M, and M the packing density, surface area of the packing, overall volume, so it's M minus 1, and AC is the cross-sectional area, M2, so this is the mass transfer area. The problem here, this equation can be used, so I can use the packing column to calculate or to find the KOG. But the problem here regarding the area. So if I have a packing, so this is the area, surrounding area of surface area. So the total of surface area is A. And it should be the interface area between the liquid phase and the gas phase. But actually, most of packing area is like they are compacted density between them. They are compacted to each other. So the area between them are very small, even liquid. There is no interface between this area. So this area, we can say it's dead area. So then the actual area is less than ideal area of the packing density. So this will affect accordingly on the KOL or the value of KOG. So in order to compensate for this problem and get accurate area, to find accurate KOL, KOG, I used another column called weighted wall column. So weighted wall column is just similar to absorption column, but it's just without any packing in it. So the liquid phase counter currently with gas phase, and it make like a film through the inner wall of the column. Then the area here will be simplified to pi dl. It's not like this. It's very simple, pi dl. So since I know the diameter and since I know the L, then I can find KOL or KOG without any mistakes. This is the objective of today's experiment. So let's go from some theory about the gas film theory. Now suppose that you have partial pressure of A. Suppose air or any element or any gas. So this gas, partial pressure of gas in the bulk, when it mass transferred into liquid through the interface, there's some resistance in the gas bulk, so the amount of gas decrease a little bit until it reaches the interface because of the gas resistance. So this is the first step. So from the bulk to the interface, we have some gas resistance. Then at the interface, the partial pressure will be in equilibrium with the molar concentration in the liquid phase. And in this part, there is no resistance. And then from the interface until it reaches a bulk again, there is another resistance, but in liquid phase. So from the molar concentration of A at the interface until it reaches a bulk, it will be some liquid resistance. Okay. Now, as you know from flux, from mass 1, the equation, the mass flux NA equal minus D times dAce, partial pressure of concentration A, d over dz plus Ca times V. V is the molecular average velocity, and it's equal to flux of A plus flux of B is if it dimolar or if it system of two components, overall the total concentration Ct. If the system equimolar, that means when Na are equal to minus Nb, so both are in the push direction, then Na plus minus Np will be 0, so this part will be 0. So this equation will be simplified into Na equal minus d diffusivity of A to B times partial Ca over dz. This part becomes 0. Okay, by integration, then Na equal, okay, this equation also we can present it in partial pressure. So it will be dAb over RT times partial pressure of air dz. By integration from PA to PAI interface and from CAI to CA, so this equation will be dAp, diffusivity from A to B, over Z at the gas phase. This is the Z, the distance from PA to PI, distance and the gas phase, times RT, and PA minus PAI. And the same for the liquid phase. It will be diffusivity from A to P, ZL, this is the ZL, and CAI to CA of the bulk. Now, there's a problem that we can't experimentally define the interface distance, ZZ or the ZL. So it's difficult to determine. So now we can convert this part into kg. So it's individual gas transfer coefficient. And also the AP over DL, it will be over individual mass transfer coefficient for the liquid phase. So we can rewrite the equation into individual mass transfer coefficient for the gas phase times PA minus PAI equal because the mass flux is same for the gas phase and liquid phase. So equal KL times CAI minus CA. And we can rearrange this equation to be PA minus PAI over CAI minus CA. That's equal to KL over KG. Okay, so now if we plot PA, okay, against CA, and suppose that the M is the linear equilibrium line between them. So if I know the slope KL over Kg, so I can determine the PAI, okay? And also I can determine the CAI. So this is the KL over Kg, the individual mass transfer for the liquid over the gas phase. So from this slope, I can find both PAI and CAI. But again, it's inaccurate and difficult to define the values of both KL and Kg. So I can use another technique just to depends only on the mass, on the M, on the equilibrium line. So PA, if I extend the line here, okay, and find the related, this one will be Ca star. So it's the theoretical concentration of A that in equilibrium with PAI. And also, if I have Ca, okay, I can find the related PA star using the M line. And it will be easier because I don't need to find both KL, the individual mass transfer coefficient. So the equation will be KOG. OG is overall mass transfer coefficient for the gas phase, A minus P star minus A star, gas, partial gas minus P star, equal to KOL for the liquid, overall mass transfer coefficient for the liquid phase, C star minus CA. Of course, if here we can, this is the PAI, and here CAI. So now PA in equilibrium with CA star, and CA is in equilibrium with PA star. Now we said for the individual, this is the individual from PA to PAI individual, and this is individual. Okay. While for overall, so we can say this one represent KG and this one represent KL. Now for overall, start from C star to CA and from PA to P star. So the individual mass transfer involved inside both individual. That means KOG include both KG individual of gas phase and individual of liquid phase, and the same thing for the KG, also vice versa. Okay. Now, so 1 over KOG, overall mass transfer coefficient, equal both KG, individual of gas, and individual of liquid, and M is the equilibrium slope. And also for 1 over KOL equal 1 over KL plus 1 over MKG. So this equation represents the overall mass transfer coefficient for both liquid phase and gas phase. Okay. Now if we have system may be liquid phase, maybe liquid phase controlled, maybe gas phase controlled, and based on the system, if it's liquid phase controlled or gas phase controlled, we can choose any of this equation. We can choose the first equation or second equation to use. Okay. Now, how to what's the importance of knowing that my system is gas phase or liquid phase? In industry, if my system is gas phase, that means I have already gas phase and liquid phase, they are countercurrent to each other. So if I want to increase the mass transfer coefficient, normally, which one I should increase, the liquid phase or the gas phase? So if my system is liquid phase controlled, so it's the best way to control the system, to control the mass transfer through the system, is by changing the liquid phase, because it's liquid phase controlled. But if my system is gas phase controlled, so the best way to control the system is to change or to control the gas phase. Okay. Now, just to understand in more detail, now we have pressure equal MC. This is the equilibrium. So the partial pressure of A equal M times C. C is the molar concentration. Now, when M increase, that means the gas is less soluble in water. This equilibrium, you can find it using Henry. It's known as Henry constant in textbooks. So when M increase, that means the system is less soluble. So P equal MC. When M increase, accordingly C will decrease. Okay. So when C decrease in solution, that means the gas is less soluble. So gas is less soluble. But when M decrease, so that means C increase or is high. So that means when the concentration in liquid increase, that means the system is the gas is very soluble in water. So with this example, for example, we have like different gases. We have HCl, we have ammonia at 2 different temperature, and we have oxygen. So as the temperature increase, the M increase, so the gas will be less soluble. Also for the HCl, the slope is very small. That means the gas is very soluble. Also for the M, the oxygen, the M is high, so that means the gas is rather insoluble in liquid. So by this is liquid phase. This can be controlled as gas phase, and gas phase. So now again, how this affect solubility of gas, how it affect on the gas phase and liquid phase. Now let's say we said P equal MC, and so C equal P over M. Now suppose that M is high. Okay, M is high. So this part of equation is significant. So when you change the C, it will be significant. That will be effect on P. Okay, so changing of concentration of the liquid will affect on the gas phase. So the system here is liquid phase control. But the same when M is high, so when it comes to this equation, it will be very small. So whatever you change, the gas phase, it will not affect on concentration. So the system can't be gas phase controlled, only liquid phase controlled. Okay, again, if we suppose that we have M is very small, that means the value of M is very small. So if you change, this part is negligible, or it has no significant effect. So when you increase or change the value of C, it still doesn't affect on the pressure. But if M is very small here, so this part is high, because when M is small here, it will be high value. So any change in the P will affect on the C as well. So in this part, it will be gas phase control. So just how to differentiate between system and how solubility affect on the system, if it's gas phase or liquid phase control. Now we finished the part of the theory, so let's go to the part of experiment and how we work with it. We already will start with our test with absorption of oxygen. We chose oxygen because it's safe. If we got any leak in the lab, it's no hazard. There's no hazard related to oxygen. But we have one problem, that liquid or water is already in equilibrium with oxygen. So in order to test the amount of KOL, we have water that is free of oxygen, or almost the amount of dissolved oxygen is minimum. So we make initial step of degassing or deoxygenation by by purging using nitrogen. So we have our water that's already in equilibrium with oxygen, so we purge it by nitrogen gas. So we strip all amount of oxygen, so then the liquid become less or in equilibrium or less equilibrium with oxygen. So when it's contact with oxygen in the column, then it can reach equilibrium again. So now we have a liquid here in our system. Liquid is water with less amount of oxygen, or that deoxygenated oxygen. And for the gas, it's just air. Air has almost 21% of oxygen. So both are counter current with each other in this column. So now we know that the flux, we said, the flux of oxygen is equal to overall mass transfer coefficient, liquid mass transfer coefficient, times saturation or equilibrium molar concentration of oxygen minus Ca. So by integration, because this one is for at each point, by integration, throw from the Ca1 to Ca2. Suppose this is the Ca1 and CO2 through the column. So it will be equal the flux overall KOL times delta CLM, the logarithmic mean. And it's equal to C star A minus CA1 minus C star A minus CA2 ln C star minus CA1 over CA star minus CA2. This is the logarithmic mean for the average concentration. Also, So we can, this is a flux. So the flow rate is just the flux times area. So it's equal to KOL times delta CLM times A. A here is the mass transfer area, is by dl. Experimentally, if I have like something measures the dissolved oxygen at the top and something to measure the dissolving oxygen out of the column, then, and I know the flow rate of the water fluid coming from the top to the bottom, so I can also calculate the molar flow rate. So molar flow rate equal to amount of water in, we can say using any volumetric unit. So you can say, for example, liter per second, okay? And this is the concentration. So the concentration here for the, we can say, for example, milligram per liter for oxygen and milligram per liter for oxygen, milligram per liter for oxygen. Then liter, of course, will times L, so it will be, the value will be in times of mg. So this is mass. So to convert from mass to mole, we divided by molar mass. So the molar mass of oxygen is 16 times 16 because it's molecular mass. So it will be 32. Then by equate both equation, we can find KOL, overall mass transfer coefficient, equal Q over area times C out minus Cn overall delta CLM. So by this we can find the overall mass transfer coefficient experimentally. Also we can find the Sherwood number. So Sherwood number, as you know, equal to mass transfer coefficient times characteristic length over diffusivity. The characteristic length is the characteristic length related to the mass transfer. And in case of piping, should be the diameter, if the flow in pipe. But here, we don't have plug flow because the flow is wetted wall. So we can say we have plug flow. So again, we have to find hydraulic diameter. So hydraulic diameter here is for area over P. A is the surface area, flow area, and P is the wetted parameter. So it will be equal to by dl over by d. So both will be cancelled. So finally, the characteristic length will be 4 times L, the height of the column. The last part is we want to validate one of our empirical formula used to correlate Sherwood number with Reynolds number. So this empirical formula is 0.433 Schmidt number, Galileo number, and Reynolds number. So if we take log Sherwood number, it will be log of all this part plus 0.4 log Reynolds number. So if I created log Sherwood number and log Reynolds number, and the slope, if the slope is 0.4, that means this equation is valid. So this is all about the theory and experiment of today. Experiment with it wall experiment, and we should now go to see the equipment and how it's work and each part, the setup and procedure of the experiment. Okay, now we'll start the experiment with the wall experiment. So we have the setup. The setup is the first column, this column used for removing the oxygen from the water. So we have the water tank, and then it's pumped into this column. And in order to remove the oxygen from the water, we have this packing, and we have this cylinder of nitrogen cylinder. This nitrogen cylinder, the gas purges purging the oxygen, so the oxygen will be removed from the water, and we can test the water, the amount of oxygen from this probe. We have the dissolved oxygen meter, and its probe connected here, so we can find that the amount of dissolved oxygen in the water that get out from the deoxygenation column is 0.7 milligram per liter. Then this water, again, it can come into as an inlet for the wetted wall column. So the water come from the enter the wetted wall column as deoxygenated water, and then we have air. We have a pump here, and the pump flow air, put air into the column counter current. So we have water from the top and air from the bottom, and as you can see, the water is flowing through the wetted wall column. Okay, so water is coming and air is counter current interact with the water. Then the outlet water can be measured here using the dissolved oxygen. So the dissolved oxygen meter here, the value is 8.15. So the value of oxygen dissolved in the water increased from 0.7 into 8, and this is almost the equilibrium amount of oxygen dissolved in water. Then again, we can change the flow rate of both water and air. So from the test, you will find that when we change the flow rate of water, so the calculated amount of overall mass transfer coefficient will be affected. Will be you can find a significant difference between them. But when we change the flow rate of air at a certain value of water flow rate, there is no big difference. There is no significant difference. That means when we change the water flow rate, KOL change, while we change air value, the KOL doesn't affect it. So that means my system is water phase control. For the experiment with change, we have different trials. For at a certain liquid, we can change the air flow rate and just wait for almost 10 to 15 minutes or 20 minutes until you get stabilized data and get your data, and then change again the value and wait until equilibrium and take the new reading. And you, by different trials, you can get different milligram per liter for inlet, outlet, and flow data from the water and for the air, liquid phase and gas phase. So that's it. The first important thing is to ensure you have a film. If this film is not continuous flow through the column, that means you have a correct. You don't have a correct area by DL. So you have to ensure it's continuous, and you have to check the data and the purging, of course, purging nitrogen. That's it. And thank you so much.